So today we have Sandra Klevansky. If you go back to the first slide.
Oh, I'm trying to. There we go. Okay.
And you can all read the title is Undetermined or Undetermined Dyson-Schwinger equation. And this is joint work with Carl and Christoph.
Yeah,
Off you go.
Well, first, let me thank you for giving us the opportunity to talk again about the work that we've been doing. And let me first say, well, I think everybody knows Carl. So Carl and I have been collaborating on this for quite a while. And Christos is also here today. And Christos is a student in Heidelberg doing his master thesis. Christos, maybe you can just say hi.
Hello.
Yeah, so everyone can see you. Right, great. All right, so some time back, Carl had given a talk about the work that we were doing, and this was at the stage when it was work in progress. And since that time, Christos has joined us, and we discovered a lot of other things that we hadn't thought about at that time. And so that's the reason why it makes sense to talk about our results now and show you some of the things that we've discovered. This does mean, however, that some of the things that I will be going through are things that you might remember from Carl's talk. Okay, so for those who were there, I can just ask you, please bear with me. There is a reason why I'm going through this again. And for those who weren't there, at least I hope that this will all become clear. All right, so the next slide, whoops, has our questions. So we started off this project by asking the question, if we could go to a higher order in solving the Dyson-Schwinger equations, would we get better results for our field theories than if we just use the lower order ones? And then what we were also after was to look to see if the Dyson-Schwinger equations behave in a different fashion if we look at non-Hermitian systems as opposed to looking at Hermitian ones. Obviously, we were looking in particular at PT symmetric systems, but we were looking to see if we could find a differentiating feature. So the way of going through this is, I'd like to start off by introducing how we look at the Dyson-Schwinger equations, how we derive them. And I would like to start out with the Hermitian phi to the fourth theory as an example, because we learn a lot of things from this and a lot of surprising things. And then it's possible to go further to see the I phi cubed. And this was somewhere around, well, some of this stuff was told by Carl last time, but this goes a lot beyond that and goes to minus phi to the fourth, minus I phi to the fifth, and also the phi to the sixth theory. And then I can talk to you about some concluding remarks. So let's have a look first at the Hermitian phi to the fourth theory as an example. All right, so the Dyson-Schwinger equations, what are they? Well, these two very bright guys, Freeman Dyson and Julian Schwinger, came up with a method of calculating connected Green's functions using only the techniques of functional analysis. And this is really very nice because it takes away all the usual difficulties that we have of having to worry about operators, where they're defined, Hilbert spaces, and all other things. So, and they're exact. And that makes them, obviously, well, should make them very powerful for us. So, what is the basic idea? the basic idea is that we start with the vacuum persistence functional, and it is functionally differentiated with respect to the source, which then leads to a field equation. And once we've got the field equation, all we have to do is take expectation values and identify the Green's functions. What usually happens is that the Green's functions are linked to higher order Green's functions in these equations. Then we set the source term j equal to 0, turning it off. And that gives us an entire series of Dyson-Schwinger equations. And what we're after are the equations for the connected Green's functions, which are, of course, related to the derivatives of the logarithm of the partition function taken with respect to the source functions. So let's go ahead and do this. Oops. Now, how do I get to the next page? There we go. So let's have a look at the conventional Hermitian-Korteweg quantum field theory in one dimension. In this case, the partition function has a reasonably simple form, and we have the interaction, which is Korteweg. Then the field equation in one dimension is obtained from directly from this. And if we take the vacuum expectation value in the presence of our source and divide by the partition function, then we get the Green's function G1 on the left-hand side here. We get something that looks a little bit strange, and we still have our source term. So our problem is simply to interpret the central term. So this is given by functionally differentiating the non-connected Green's function, gamma, which we've denoted with gamma. And this thing is simply, by definition, a product of the partition function multiplied by the Green's function G1. So we can look at the next non-connected full Green's function simply by differentiation of the right-hand side of this. We obtained here two different terms. And then we can continue this process, and the one that we really want in this case is gamma 3, which is this guy that was in the field equation, and this has several terms with G1, G2, and G3 all occurring in them. Philip, you have a question.
Yes. Are the J's quantum operators or classical operators?
These are sources. So
yes.
this is just a number.
Okay.
This is a function.
Yes.
A functional.
The reason I'm asking is you seem not to have got time ordering, because if you do the derivative with respect to J1 and then J2, you would claim to get the expectation value of phi1, phi2. But then if you do the differentiation with respect to J2, J1, you get the vacuum value of phi2, phi1, and then you've shown that they're equal.
Oh.
So that's why usually the path integral gives you the time ordered product and not the 2-point function.
No, that's not true.
Oh, so why they're not equal?
So we can't in this, during the space of this talk, go through it. But
Okay.
Schwinger has in his papers, he shows that J is a C number source. And if you differentiate, functionally differentiate with respect to the C number source and carefully use the Green's functions, automatically what you end up with is time ordered products, okay? And the derivation is long, and we can talk about it afterward, but the bottom line is that number one, J is a C number source, not an operator source. Otherwise, it becomes very difficult to define what you mean by differentiating with respect to it. Okay, and secondly, this derivation is formal, but it is correct.
No, I'm happy that it should be the T product. It's just that you've written down vacuum phi squared or vacuum phi cubed without time ordering.
That's right, because those fields are all taken at one point. So it doesn't matter.
Yeah, that's the point.
It doesn't make any difference. These are the expectation values of phi of t times phi of t times phi of t. Okay, so in this particular case, it's an irrelevant issue.
Okay. All
But
right.
it would come out correctly if you did the full thing.
If you did phi of t prime.
Mm-hmm.
Yes. Okay, that was all I was asking about.
Yeah.
Yes.
Good.
Thank you. That's fine.
Okay.
Peter
can I
also has a question.
Doesn't it get problems if you take these functions at equal arguments? T equals T1 equals T2. If I do it in quantum field theory, I have distributions and then I get delta functions, and taking them at equal time will lead to divergences, no?
Oh, Carl, do you want to answer?
Yeah, we're working in one dimension, so this is not an issue. And we're working in basically in one dimension and zero dimension. And this is simply not an issue. Nothing becomes singular until you go into higher dimension.
But it does
Okay,
become a problem.
G of t and t is a perfectly well-defined finite quantity that requires no such renormalization at all. And this is not the issue of the talk. The question of using the Dyson-Schwinger equations in higher dimension, what I don't want to give away the message of this talk, but going to higher dimension is not the issue. The issue is getting to the Schwinger-Dyson equations to work at all. That's the issue.
Yeah. And you will find, Frida, you will find problems, obviously, if you go to higher dimensions. Okay. So let me just stick with this and say, so this, this thing is kind of jumping a little bit where I don't want it to. Okay. All right, so there we are. And we can take this middle, this was the middle term, which had to be divided by j. And if we substitute it in, then we get this equation, which is our first equation. Then we have to set j to 0. And this essentially will give us the first Dyson-Schwinger equation. Okay, so we have translational invariance if we set j to 0, and so we have an equation which looks like this thing that is here on the right-hand side. Now this thing looks like a problem anyway. To continue further, this equation that I'd written down needs to be differentiated again with respect to j of t. If I do that, then I get the equation that has the equation of motion for G2. And this contains then a lot of terms that have G1, G2, G3, and G4 in them. Okay. And then once again, set j equal to 0, restore translational invariance, and one has 1 second Dyson-Schwinger equation. Now, what you notice here is that this is one equation and it has 4 unknowns. So of course you can't do anything with it. So the first thing that you can do is you can say, and this is what we usually do in field theory, is we say the higher order correlation functions, G3 and G4, are simply 0. We truncate. And what this does is it leaves us with an equation that at least looks like something that we can solve, that we know from somewhere else. So this is the standard equation that you would have for G2, which is now solvable. And in particular, if you consider that we are looking at a quartic quantum field theory, then in fact, you would also set G1 equal to 0 because of parity symmetry. So in fact, you can solve this, and then you have an exact solution for G2, and this G2 at t equals 0 is 1 over 2m. So you've got the answer. Now, what we've done is we've chosen G equal to 1. And so the actual value for m can be calculated, and one finds a value of 1.145. Now, the exact answer, if you calculate that for this system, turns out to be 1.088. So this is a little bit high, but this isn't so bad because we're talking about a leading order truncation. Okay, so if we were, on the other hand, to take this exact same set of equations, but look at the PT symmetric quartic theory, then of course we couldn't set G1 equal to 0 because this parity symmetry in itself isn't there. So we have 3 simultaneous equations. And if we solve these 3 simultaneous equations, we wind up finding a value for m of 1.442. And if we look at the exact calculation, it doesn't look particularly good. So the question that we need to ask ourselves is, can we do better if we go to higher order in the Dyson-Schwinger equations? That is our next question. So we already had, we go back to the Hermitian quartic theory, but I've still left G1 in this, okay? And I've written down the four first occurring equations, Dyson-Schwinger equations that you get. And what you can see in this is that the first equation has 3 unknowns. The second equation has 5 unknowns because now we've gotten G3 and G4. The next one introduces has G4, G5, and then we have in the next one G6 coming along. So we're always getting more and more unknowns coming into this. And then, of course, what we can do is we can say, okay, we're in the Hermitian quartic theory, so it becomes a little simpler if we regard parity invariance, because then all the odd Green's functions vanish. And what we can do is reorganize the equations in such a way that the highest G is on the left-hand side, and then you can see that G4 is related to G2. G6 is related to G4 and G2. G8 is related to 6, 4, and 2. 10 is related to 8, 6, 4, and 2. Okay, so it has a very interesting structure, but it's always underdetermined. We always have at least one more unknown than the number of equations. So these equations have to be truncated in some fashion in order for us to solve them. So one way of doing this is to make this first truncation, and the first truncation would be to say we set G4, G6, G8, G10, all of the G's equal to 0. That is our first assumption, which would then give us the equation to solve minus 3G2 squared plus 1 is 0. So we would then know that. The second truncation that we could choose is simply set G6 equal to G8 equal to G10 equal to 0. If we do that, then we know G4. So we can insert G4 into the second equation, which would mean we have a different equation for G2, but we can solve this and set it equal to 0. And we can continue in this fashion. So if we want to truncate, make a third truncation, we could set G8 and G10 and all the rest equal to 0, in which case we would insert G4 into G6. So we would have a function only of G2, and then we would insert this G6 into G8, and we would have a polynomial equation again as a function of G2, set that equal to 0, and that's the answer, and look for the solutions of that. Okay, so what we do by doing this, what we're doing is developing a polynomial structure in powers of in G2. Okay, and what it turns out is that we are then having to solve these polynomials equal to 0. So this would be our first truncation would be to solve P2 equal to 0. The second would be to solve P3 equal to 0. The second would be to solve P4 equal to 0, etc. Okay. Now, this might remind you a little bit of something like Taylor expansions, where you go to higher order, you get better approximations. But at the same time, you know that you develop a tremendous number of solutions, and it's not really clear what the right one is. So let's go ahead and go to the next transparency and say, well, supposing we did the first one, we got this approximate result. We can compare it with the exact result. It's not brilliant. Okay, so what happens if we go further? So for every order that we get, we start generating a number of solutions because we have different polynomials that we have to set equal to 0. What I have done is I've plotted the exact result as the red line. And what you notice are a couple of things. The first thing is that going maybe up to about 10 or something like that, that was the stage at which we were talking last when Carl was talking about this problem. And you can see we were getting very, very happy because we thought to ourselves, we are getting there. This process is working. And what we are noticing are two different things. We notice firstly that there is kind of a large density of roots near where the exact answer is. It's the first thing we notice. And the second thing we notice is that the things are monotone. And of course, this is where Christos comes in. And Christos does all these calculations and more, and discovers that, together with all of us, that these dots have a limiting value. This limiting value you can get by extrapolation, and the limiting value lies at a value which is in fact below the exact value. So in other words, solving the Schwinger-Dyson equations in this fashion does not convert to the actual exact value. So what else do we see? We also see that the zeros of the successive polynomials interlace. So one might have thought they were orthogonal polynomials, but in fact this doesn't happen, that they're not orthogonal polynomials. But really this is the problem, that we find that the limiting value lies below the exact value. So the question is, what on earth is going on? Okay, and can we in fact do better? So I'm going to show you how we can do better. The first thing is we know G2 exactly. And because we know G2 exactly, and the Dyson-Schwinger equations are exact, we can therefore use this value of G2 to calculate the exact value of G4 and the exact value of G6, and we can calculate all the values exactly. Okay, so we do this. And so I've written down these values in blue on the right-hand side of each of these equations. This is extremely strange because what you see here are that these numbers, okay, they oscillate in sign. That's one of the things that you also notice. But the other thing is they grow. And if you're getting to something like G18 or G20 or G22, you're looking at extremely large numbers. So the first thing is it's amazing that this whole procedure works anyway, because we set everything equal to 0. So the question is, can we do better than setting these numbers equal to 0? And what we then did was we looked to see how the GN behave asymptotically. Okay, and the asymptotic behavior is governed by this. Well, firstly, there is this factor in which each one changes sign that we've seen from the last slide. There is also an extreme growth. This is factorial. And then there's a factor which we don't know about, some constant. And it turns out that simply from numerics, we discovered that this constant has this value of 0.4095057. The question is, who ordered that? Yeah.
Is this a generic result for G2N, where the only thing that G2 does is fix the role of R, or does it actually fix the dependence on N?
It fixes the dependence on N for this theory, okay? And R is a constant. It's a fixed constant.
No,
This number that you're talking about, this number 0.4, is not a G2 number. This
okay.
is here. What Sandra is talking about is the asymptotic behavior. The second red line on her slide is the asymptotic behavior of G sub 2n. This is the nth connected, okay, the nth Green's function, okay? And this is from the exact value, you can do an asymptotic fit, and this number comes out in the fit.
So it's independent of the value of G2. That's what I'm asking.
No, this is the exact, this comes from knowing the exact value of G2,
it's because G2
which
is
tells us the exact value of G4 and G6 and so on.
Right, I mean, we had the exact values, and so from that we can determine how this looks. Okay, so the question is, can one understand this a little better? Which is, in fact, the question. Well, the first thing is, if we were to start by rather putting in the asymptotic values for G2, then we get terrific agreement and very, very fast with the actual calculation, with the actual exact value of G2. So this works extremely well. But how can one justify this? And maybe this helps understand this better. One of the things you can do is you can say, well, let us kind of extract the behavior that we've kind of seen by taking out the minus sign, by taking out the factorial, and saying we have some function left over. Okay, then obviously the Dyson-Schwinger equations change slightly, and they have this particular form. Okay, and if you look at this form long enough, you will see a structure in it. And the structure in it will enable you to define a generating functional, which a generating function u of x for these coefficients g2n. So u of x is given by x times little g2 plus x cubed times little g4 plus x to the 5 times little g6, etc. Okay. Now, you can see that this is correct. I can just go through one example. Oops. This satisfies the equation, the second order differential equation. U double prime of x is this on the right-hand side. And you can see this, for example, easily for the first equation, because look at the coefficient of x. This equation must be valid for all powers of x. So let's take the coefficient of x to the 1. Okay. So taking the second derivative of u double prime will give me 3 times 2. Okay, that's the 6 occurring here. Clearly, for the G6, it will be 5 times 4. And that would be the 20. Okay, so you're starting to see that the second derivative generates what happens on the left-hand side. If you look at the right-hand side, then the power of x that is 1 can only come, can yields this 1 here. Okay, whereas the u cubed term cannot have a power of x because the lowest term would be x cubed. And the factor 3g2 squared comes simply from the 3 here and the g2 squared from u times the derivative. Okay, so you can justify this equation contains all the Dyson-Schwinger equations in it, so as to speak, as a generating functional. So the question is, can you actually solve this? And yes, you can. If you make the substitution of u being minus y prime over y, then the equation looks Riccati-like with similar boundary conditions. Okay, and so the question then is, can you solve this equation? Philip is asking a question again. Philip? Or was that from last time?
I think it was from the last time.
Okay, right. Okay, so in fact, you can solve this, and the equation for y, the solution for y, is a cosine transform. Now, if y passes through 0, then u becomes infinite. So this value of x determines the radius of convergence of the series. And the first time that that happens, at least when x is positive, is at the value plus 2.44, or in fact, the radius of convergence is exactly this number, 0.409506. Okay, so that's where it comes from. So we can even understand why this asymptotic approximation, why this number comes out in our asymptotic approximation. Now, one of the other things is, of course, Christos tried all sorts of other things, all sorts of other types of approximations for Gn to try and see if you could get a better approximation without knowing the asymptotic approximation. Okay, but I hate to say it, the other approximations that we tried out, they did a little better, but they certainly did not converge to the correct answer. Okay, so obviously, so that was one of the things that we discovered. And here we're only talking about the Hermitian theory. I mean, we're not even talking about PT symmetry. We're not even talking about non-Hermitian stuff. So this was a big surprise for us. Okay, so then the next thing is, let's move on to I-phi cubed. Right, so here we would do exactly the same procedure. We would set higher order GNs to 0. We would solve for G1. Of course, we would derive the equation of motion and all the Green's functions with this new interaction, and working up to n equal to 150, plot what we get. And the value that we would expect for G1, if we calculate it exactly, which we can do, is minus 0.729. And what we find is that on this negative axis, we discover that we have a kind of bubble that develops, and it develops around the value that we're looking at, but it doesn't get there. The other thing you notice is that there is this threefold symmetry, and the threefold symmetry is also a result of the fact that we're looking at I-phi cubed. So just to see a little bit more of this, what I have done is I've also plotted just the values from one order, namely order n equals 150. And I've just plotted them as positive numbers. And you see that this is a very clear, pretty loop, which does not, even at that order, does not actually get to the actual answer. Okay, so the question is, what does? Well, we've had all of this experience with the asymptotic approximation that was made for phi to the fourth. So that is the next thing to try out. And in this case, for the non-Hermitian cubic theory, in fact, the asymptotic solution, which are these blue dots, which first oscillate around the correct value, then continue to give the correct value, but at the same time, we find a value that is above and a value that is below. So in other words, if you're thinking diving down the imaginary axis on this picture corresponds to moving up here. So you're moving, so you're moving up this axis. Then this bubble occurs, and you see there is a value in the middle, which has now come in, but there's also value at the top. So our bubble is still there, but it has an exact value in the middle. In fact, it looks more complicated if you look at it in the complex plane. It's a very pretty picture. Okay. And once again, the question is, how do the Green's functions behave asymptotically? And in this case, it's a little different to the previous one, but of course we can determine it in exactly the same way. So I won't go into any detail on this one, but just say that we find a value here, a similar sort of asymptotic behavior. So there is also a power. In this case, there is also factorial, and there are changes of signs, but this is related also to I. So finally, we have found a way of actually getting the correct answer. All right, so now we could think about what does the non-Hermitian quartic theory minus phi to the fourth do? And of course, naively, what we might have thought is, well, if for phi cubed, we've got nice bubbles occurring in a threefold symmetry, wouldn't a minus phi to the fourth give us nice bubbles occurring in fourfold symmetry? Unfortunately, that doesn't happen. But the result is also very interesting, okay? The difference here is that here, when you go to quartic or higher order theories, you're not solving one equation, you now have to solve at least two coupled equations. And so it becomes far more difficult to solve in the first place. And the second thing is that because of this and the specific types of solutions that you can get for coupled equations, you get a more complicated structure in the complex plane. So what we are finding is that we are getting this similar features to the features that we have found before, namely that we get clustering around the correct values, in this case, minus 0.977, so you can see it here. And also there is a fourfold symmetry. So that's not unexpected, but it's not this precisely clean structure that one sees when you're solving a single equation. So one can go even further. If, for example, we solve the theory for the quintic equation, then we unfortunately now have to solve three coupled equations. So this becomes also, in the way that you solve it, more complicated. And the exact values which we can calculate are firstly, well, I think the standard one is lies on the negative imaginary axis. I should point out there is also one which lies on the positive axis. And I have, Christos has put the exact values as red squares on this diagram. So what are these all? Well, of course, it depends on the path that you take in the complex plane in order to actually calculate your Green's functions. So, for example, this is the traditional path that is PT symmetric, which goes from this left-hand side through to the right-hand side, but that's not the only possibility. The other possibility, well, another possibility would be this particular choice. I should say, of course, the green areas in this graph represent the areas in which the theory converges. But of course, there are also a lot of others. I mean, I could have integrated from there to there. And if I had done that, I would have gotten a complex value for doing this. And the interesting thing about this, if I go back to this picture here, is that all of these values are present in the Dyson-Schwinger equations. So the Dyson-Schwinger equations seem to know about all the solutions of all the Stokes sectors. Okay, so then the last example that I've brought along is the one of the full Hermitian sextic theory. In this case, we've imposed parity symmetry simply because it makes it a little bit simpler. But this leads to four coupled polynomial equations which have to be solved simultaneously. And if you do that, then you see a similar structure to the structure that we had found for the phi to the fourth. So if you're looking along the real axis here, you see that there are solutions which are approaching the actual exact solution monotonically, but they're not getting there. Okay.
I think
Um,
Philip has a new question.
Yes,
Philip.
going back to the Stokes sectors, and you said that the Schwinger-Dyson equation knows about them. Isn't this the same issue as going back to the original d phi integral and asking what is the domain of phi in the complex plane for which the integral actually exists?
Yes, it is.
Yes,
But yes, it is. But the
yes.
fact is, you're not doing that. When you actually look at your Schwinger-Dyson equations, you haven't actually imposed any boundary conditions. You haven't said anything. Okay. But
Well, you have. I mean, you've presupposed that the integral that you derived it from exists.
yes, you presume that it exists. That's
Yes,
right.
and this is then revealing to you under what
Yeah.
conditions it does.
Yeah. So it's doing it automatically. Whereas, of course, if you're actually going through this procedure, then you're actually specifying the boundary conditions and integrating. Frida.
Well, in your generating functional, there appears the product of phi and j, the source. And now changing to another phi, which has a complex factor, the source picks up a complex constant, and the phase integral will somehow produce also some factor. So by rephasing the fields by complex constants, I think you somehow get a certain symmetry in the result of your integral, which you will see if you put the source to 0, because then the complex factor which the source has picked up will disappear. Yeah? So rephasing the fields in the path integral will produce a complex factor to the source, and as when you in the end send the source to 0, then you can play with the symmetry which your path integral has, and so the whole result will have, the whole picture will have a certain symmetry. No.
Well, we're not actually rephasing any fields.
No, you said in the equations, in a sense, you see all sectors where the integrals converge, but this means the whole path integral itself has a certain symmetry inside, which produces these sectors where the integral converges, and this is somehow inherent in the integrand of your path integral, because you can rephase your source, and then you will somehow make a move to a different Stokes sector, or not?
No, that's not true. That's not true. Can I make a comment there? This is very important. When you derive the Schwinger-Dyson equations, the entire operation is local. This has nothing to do with infinity. It has nothing to do whatsoever with points other than the point where you are differentiating, where you are functionally differentiating. The derivation of the Schwinger-Dyson equations is a local derivation. It has nothing to do with infinity. The only assumption is,
you obtain the equations by the limit of
the only assumption that you are making is that the integral exists, and so therefore you derive a system of Schwinger-Dyson equations. Now you go through the entire procedure that was described in this talk, okay, and you end up with a set of polynomials, and you find those zeros, okay, and those zeros are supposed to be the value of the Green's function, and there are zillions and zillions of dots, okay, and you see concentrations of dots, and there's a concentration for each different way in which the integral could converge, but in the derivation of the Schwinger-Dyson equations, no such fact was being used. They're the same Schwinger-Dyson equations regardless of which set of Stokes sectors you're using. It has nothing to do with the
Yeah,
Stokes
but
sector.
you obtain the equations by taking the limit of j equals 0.
Correct.
And this
Correct.
means
That's a local process. We're not letting anything go to infinity. We're setting j equal to 0.
But this limit somehow, as long as you have not taken it, it breaks a certain symmetry. And when you return to j equals 0, somehow you restore the symmetry. So the equations contain the full symmetry of your path integral somehow.
That is all that has been said in this talk.
Mhm.
Okay, what you see is that all of the dots exhibit a symmetric pattern, which could be 5-fold symmetry or 6-fold symmetry. And that is because the original Lagrangian had that symmetry. Okay, but it has nothing to do with which Stokes sector you are defining your theory in.
Okay,
It gives you the solution in all theories.
yeah.
The Schwinger-Dyson equations are smart in that sense. They don't care which theory you want to talk about. It's going to tell you the solution for every single theory, for every possible theory that you would like to study.
Yeah, if I can very quickly add to Friedel, it is necessary that before you switch off J, that the J phi term be PT symmetric.
Sure.
Yes, and that is an imposition, but it's a mild one, but it has to. So in other words, if you want to make any transformation on the fields, you have to do it in a way that the source term retains the PT symmetry.
Right. That's true.
But we're
But
not
that is always assumed.
Yeah. So I mean, the point about just bringing out the Stokes sectors was simply to understand what those values were and to be happy that we have the right values and to understand that, in fact, these concentrations of dots are, in fact, the right answers that come from these different Stokes sectors. So in reality, nobody wants to calculate this. Okay, in a field theory, we want to sit with the Schwinger-Dyson equations because that's much more comfortable to work with. Okay, so as I was saying, if you then look at the Hermitian sextic theory, then in fact, just maybe repeat myself, the interesting point about this one is that in fact, it behaves very similarly to the phi to the fourth, because you can see along the real axis, you're getting this concentration of values which are coming monotonically from below, and they're not reaching the exact value. So the only way probably to get this exact value would be, once again, to do an asymptotic approximation for this. Okay. So, in total, what happens? What have we found? Well, the first thing is that, interestingly enough, these Schwinger-Dyson equations know all about all of the solutions. So without thinking about where does this converge and how does this behave and all the rest of it, we have all the solutions. The second thing is that well, I think one of the things which I don't like very much about it is that, of course, in the examples that we had, we knew the exact answer, but of course, what was happening was we were finding that we get a lot of answers, a lot of extraneous answers, which are not the answers that we're looking for. And we find that there is a bundling of solutions where we think the real answer is. So that's, for us, an indication of where to look for the correct answer. If we use our truncation scheme, which has least bias, which I think everybody does, set Green's functions to 0, it converges to a wrong answer. That's crazy. But this answer is pretty good. and it's near the correct answer. So it's amazing that it works. But if we really want to get correct answers, then any other forms of truncation schemes other than starting out with asymptotic values won't give us good results. And the asymptotic values give us excellent results. And in fact, it does it also very, very fast. So instead of having to churn up to 30, 60, 100, 150 terms, one generally only needs something like 5. And then we have the right answer. So it's difficult to generalize it to higher dimension. We're thinking about this and we think we know how to get a little bit ahead of this on this. But it's quite amazing. Okay, so I think that in fact was all that I wanted to say for today. And just say thank you for your attention. And if there are any further comments or whatever, we can discuss them now.
Thank you very much, Sandra. Thank you.
Thank you very much.
Questions, comments?
May I ask if the truncation from the higher end looks pretty bad because is a diverging series? Can we truncate all sort of like from lower end, like setting G2 equal to 0?
If you set G2 equal to 0, then you have a physical problem because the inverse of G2 is a mass.
Oh, I see. There may be varying G2 to see if it's just working backward, varying G2 to see if the real value of G2 has any attraction being a fixed point or something like that.
That might be an approach. I mean, variational schemes usually give very good results. Okay, without actually understanding why they do. So that is definitely maybe an avenue that one could explore.
That's a good idea.
Yeah.
Thank you.
Philip.
Yes, I have 3 comments. One is about the failure to get a good answer when you did the truncation. If you do PT theory, then you're calculating it in a vacuum where you use the C operator. And the C operator changes in perturbation theory. And I'm wondering if that might compensate in some way. That's my question. That's the first question. The second, okay, well, maybe you comment on that one first, and then I'll ask my second.
Yeah, you know, the C operator doesn't enter into this field theory directly. So that is one of the beauties of this formulation within path integral formalism. You don't have to worry about it. So something like that should kind of be built in automatically. I mean, going back to an operator formalism, is precisely the thing we don't want to do.
No, I understand that. I'm just asking whether you may have missed something by doing it the way you're doing it. I'm not saying you have. I'm just saying you may.
I don't think so, because remember that the first place in which we were doing this was for a Hermitian theory, because we were convinced that the Hermitian theory should work. Our point of starting was to say, well, we need something to understand what the differences are between Hermitian and non-Hermitian. So let's start with the Hermitian one. And it was precisely the Hermitian one that didn't converge to the right number.
Okay, that was my first comment. Second comment is, there was a paper by Callan, Jakeef and Tomboulis back in the 1970s, derived the Schwinger-Dyson equation using a functional formalism with a bilocal source. not just J of X, but J of X and X prime. And I don't know whether that might prove useful for you. That's just a comment. Now, the third comment was a little bit maybe related to King Hai's question. There is a known exact solution to the Schwinger-Dyson equation in 3+1 in quantum electrodynamics, where you take the photon to never dress. So you use a Bohr photon, but you dress the propagator and you dress the vertices. And Johnson, Baker, and Willey, way back in the 1960s, showed that the exact solution for the fermion self-energy is P to a power. And that's an exact result. And that P to a power, you can write it as e to the gamma log P. And if you expand it as a power series, you get log squared and so on. But only if you sum the entire series do you get the power. So this is a thing that you can't truncate. And so I'm wondering whether that might, and of course, later on, it was realized that if the photon is dressed, it's because you have a fixed, it is not dressed, it's because you do have a fixed point. So I'm wondering that might prove helpful to you.
That's an interesting comment. That's an interesting comment.
The only problem there, Philip, is that, you know, that's only, that uses only the very first Schwinger-Dyson equation, or the first two, if you want. But what we are looking at here is what happens when you try to combine all of the Schwinger-Dyson equations. What happens as you add more and more? Do you get a better answer? And the answer is you do get a better answer, but you never get the correct answer. That was so what this talk was about, was that I mean, you know, in low dimension, that's the only place where you can study the Schwinger-Dyson equation, you know, way out to nth order. Okay, in a real field theory, going beyond second order is hopeless.
Okay, so what you're saying,
just because the Schwinger-Dyson equation now becomes a differential integral equation, which is very hard to solve.
Well,
so Carl, you're saying in this thing which Philip is talking about, that there is an implicit truncation anyway of higher order Green's functions.
Yeah.
Okay. Okay. So that doesn't help. Okay.
Right, but it's sort of like taking classes of Feynman diagrams and dropping them, but keeping other classes of Feynman diagrams. So Feynman diagrams that involve dressing, maybe we should ignore those, but the rest of the Feynman diagrams we keep. I mean, this is connected, Philip, with combining the Schwinger-Dyson equations with a weak coupling expansion. Okay, and this talk today specifically didn't cover anything about weak coupling expansions inside of the Schwinger-Dyson equation.
No, it was not a weak coupling expansion.
Well, but you're treating the coupling constant alpha as small.
No.
Okay. Otherwise, what do you mean by dressing?
The photon doesn't get dressed because you're at a fixed point. But we don't know that the fixed point occurs for 1/137.
Right, but the point is that dressing is a process that you understand in a diagrammatic sense. So it's like you're throwing at a class of graphs. Okay, here we're not. Here G is large, so it's not. Okay, it's unclear. It's a complicated question.
I'll give you a different example where there's no truncation at all. There's an exact solution to the Tiering model in 1+1, and it scales with an anomalous dimension. Now, for the Tiering model, there is no coupling constant renormalization. So the beta function is identically 0, independent of the value of the coupling constant. And therefore, it's exact for all strengths of the coupling constant. So that's a case where you can actually solve the Schwinger-Dyson equation exactly.
Yes, that's because the theory is trivial.
It's not trivial.
Well, it's trivial. I mean, it
took Ken Johnson to solve it.
right, but it's a non-interacting, it's a trivial theory. I mean, it's a free theory, basically, with some renormalizations occurring. So, you know, but it's basically a free theory.
Well, maybe I could just make one other comment. You know, on the one hand, it is surprising because I mean, I was thinking at the time of, you know, just going to higher orders with series must give you a better result. You know, why doesn't it do that? But on the other hand, we also know that from critical phenomena theory, that there are certain approximations that you can make. They never give you the right critical exponents, never do. So, you know, often there you need something really special in order to get very exact results. So maybe this is, you know, just reminds me a little bit of that this is saying very clearly, rather try and solve your theory asymptotically. And if you can, then you have a good chance of being able to solve it in other areas, in other regions.
Can I make just one remark? The big result that is presented here, the really big result is this. The Schwinger-Dyson equations are fundamentally underdetermined, okay? So there's a problem, okay? And any procedure that simply sets the higher Green's functions equal to 0 or tries to make some approximation, you know, to some mean field like approximation, something like that, doesn't work. Nothing like that works, except for one. The one thing that actually works is if you can determine the asymptotic behavior of the nth Green's function for large n. Okay, and we believe that in general, this could be done. It certainly can be done in 0 dimensions, but we think that this is an interesting new asymptotic limit that hasn't been studied, okay? And once you know that, so you don't set the higher Green's functions equal to 0, you merely replace the higher Green's functions in the Schwinger-Dyson equation by their asymptotic values, which can be found. And now if you solve the Schwinger-Dyson equations, you get the right answer. So that is enough to give you the right answer instead of the wrong answer, okay? And that is the main new result, which I think is extremely interesting, okay? Because this is, as I say, a new asymptotic problem to be solved, generic problem to be solved in essentially any field theory, okay? And I think it can be solved.
But that may require some knowledge to really find the asymptotic behavior of Green's function. That may not be trivial. For example, in Carl, when we wrote my first paper with you, we did this for eigenvalues, and for higher order of eigenvalues, we use WKB, and the lower one use numerical, and we put them together. They fit fantastically well.
Right.
Which means in that case, we do need the WKB method to give us the asymptotic behavior.
That's correct.
And here we probably need something.
Yes, indeed, absolutely. You need to do a semi-classical approximation to the functional integral that defines the nth Green's function for large n, okay? And this is almost identical to the calculation, to calculating the asymptotic behavior of gamma of n for large n. It's almost exactly the same thing, right? The gamma function is defined by an integral, and under the integral sign is an exponential, which you can think of as an exponential of the action times the power of x.
Yeah.
Okay, and that power of x is now getting large. So this is like the derivation of the Stirling series, and that is indeed a semi-classical approximation. Okay, that's the whole point. So you've put your finger on it, and you are right. And this is the point, that once you know that asymptotic behavior, the fact that the Schwinger-Dyson equations are underdetermined has been overcome. So you don't throw away what you don't know, but you put in its approximate asymptotic behavior.
You're actually using the infinite one as to determine the series.
Exactly right.
Mhm.
That's the point. So it's a whole new approach to what you do to solve the Schwinger-Dyson equations.
Frieda.
Yeah, but Carl, if you do the semi-classical approximation in the former sense, then you break somehow these symmetries which are inherent in the path integral. If you do the semi-classical approximation in a way how you did it with Jones together, then you keep it. Yeah, so it's very important to do it in a way how you did it with Hugh Jones.
Indeed.
Where you connected all these turning points with integrals, yeah, and not just keeping one integral.
Yeah, we think that in the approximations that we've made, we have maintained all of the symmetries of the underlying Lagrangian or Hamiltonian. Okay, but that's absolutely true. Any approximation that violates the symmetries of the theory
is not good.
Is not a good idea.
But
although that's exactly what you do, for example, in electrodynamics, when you do some calculations and you violate gauge invariance, and then you have to do something about that. Okay, because the original Lagrangian has gauge invariance, but when you start calculating, you may be fixing a gauge and so on. So
it could be that the truncation destroys also the symmetry.
No, it doesn't. That's the point. It doesn't.
I mean, the question is, what is a truncation? Either setting a Green's function to 0 or somehow multiplying the integrand of your path integral by some function which somehow in a certain limit changes the results, no?
I don't know what you mean. Nobody multiplied the integrand by
in nuclear physics, very often integrals are somehow not going to infinity, but you multiply them by a theta function where you cut them off, or I don't know what, to get a finite result, or you're multiplying by
none of that
damping or something like that.
I don't think any of that is relevant here, because that's not what is being done.
But I suspect, I think what you found is should not be just the property of Dyson equation. I think many algebraic this iteration may have this problem.
Yes,
truncation, and if you show it's a divergent series, then when you do truncation, then that iteration, it would probably have a similar problem. This may be a generic feature.
It is. It absolutely is. When you, independent of the Schwinger-Dyson equations, when you are solving for the roots of large polynomials, this is a very, very unstable process. Yes. Okay, Wilkinson has talked about this in his work. That's absolutely right. And here you're fighting with that instability. That's the problem. Okay, you are completely correct. The Schwinger-Dyson equations are important in physics, but this goes way beyond that. Yep. Yes, you're completely correct. Absolutely right. You've nailed it.
I think that's a good point to stop, no?
Great.
We had lots of questions. Thanks again, Sandra. Thank you very much. Thank you.
Yeah, thank you to everyone, and also thank you Carl and Christos also for being there for the discussion.
Thank you, everybody.
Sandra,